Hello, everyone. Thank you for coming. This is Brkcrs 3810. Hopefully, everybody is in the right room. Right. So my name is Satish Kondalam. I am a technical marketing engineer in the enterprise switching team. My focus primarily has been on software-defined access. So today's session is going to be a technical deep dive on software-defined access. When I actually created the session and I looked at the report today, there are about 250 folks who want to actually learn packet walks in a software-defined world, right? And I'm like, wow, a lot of people want to come and actually learn, the deep dive packet walks, right? So if you look at the session today, this session is primarily focused on the fabric. We are going to go deep into the fabric on how does the forwarding work in the fabric, how does the control plane work in the fabric, and so on. We do not deal with other components of software-defined access, right, like DNA center, eyes, and other things. It's pure fabric in architecture, fabric infrastructure, and the associated packet walks. Before I start, I wanted to get your attention to this subway map. This session is right here. How many of you attended 2810 in the morning today? So 50% of it. Again, please note this is a 3000 level series. That means that the expectation is you understand a little bit of software-defined access. I'm not going to cover any of the basics of software-defined access, which is covered in 2810. I'm going to assume that people in the room know about SDA, are familiar with SDA, and want to understand the deep dive or the deep architecture of SDA. So again, just wanted to reiterate, we are not going to cover the other elements of software-defined access, like your DNA center, your eyes. Those pieces are not covered in this session. Right? So with that, let's get on to the agenda. So we are going to start and talk maybe 5 to 10 minutes about the different roles in the fabric, like your fabric edge node, your fabric border node, your fabric control plane node, just a very high-level introduction to them. Then we are going to talk about the forwarding in the fabric. Right? So before you even start forwarding in any network, you need an IP address. So we're going to talk about how DHCP works in Fabric, some of the innovations we have done in DHCP to make it work with software-defined access Fabric. Then we are going to talk about the control plane interworking. How does the Lisp control plane work in Fabric? Then we are going to talk about the unicast packet forwarding and the multicast packet forwarding. Right? Again, everything that we need in the Fabric infrastructure to make software-defined access work. Right. So let's start with the Fabric roles and constructs. Right. So we have our SDA Fabric here. And on the top, we have our automation tool. We have our assurance tool. So together, the automation engine and the assurance engine is what is Cisco DNA Center. Okay. Then we have our control plane nodes here. We have our fabric border nodes. We have our fabric edge nodes. Right. And then we have our fabric wireless controller. These are the components of your software-defined access, your DNA center, your eyes, your border node, control plane node, and edge nodes. Our focus in this session is going to be primarily here, right? How does your endpoints in the fabric talk to each other? How does multicast forwarding here work? How does the unicast forwarding here work? How does your wireless traffic work in SDA? Right? Okay. So before we go there, a little more fundamentals of software-defined access. SDA is a fabric architecture, meaning there is an underlay, there is an overlay. Your underlay network has all your network devices connected to it and has an underlay control plane. In SDA, the underlay control plane is ISIS. Right? And then you have your overlay network, where now your edge devices communicate in the overlay network, and then there is an overlay control plane in the network and an overlay data plane. In SDA, the overlay control plane is Lisp. The data plane is VXLAN. Okay. So let's take a look at what is a control plane node. A control plane node in SDA is the entire brain of the system. Right? It registers all the endpoints in the fabric. It is responsible to ensure that endpoint 1 and endpoint 2 can communicate in the fabric. Right? So that's my control plane node. Edge nodes. Edge nodes in fabric is responsible for your endpoint connectivity. Things like your wired endpoint, things like your IoT endpoint, all of these things are connected to an edge node. It is also responsible for authentication, like .1x, like MAB, all the authentication also happens on the edge node. Border node. There are 3 types of border nodes in the fabric. One is an internal border, aka rest of the company border. Has anyone played around the DNA Center UI in the room? About 20%. So for you folks, you would probably know this because the moment you go to your border, add a border to fabric, you have 3 options there. One is your rest of the company, internal border. The other one is the outside world, external border. And the final type is anywhere border, which is both a combination of internal plus external border. Okay. So what is the internal or the rest of the company border? So the border is your exit point and entry point into the fabric. If you want to, let's say, connect to data center from your campus, let's say if you want to connect to WAN from your campus, these are known networks in your company. So if you want to connect to known networks in your company, you use the internal border or the rest of the company border. If you want to connect to unknown networks in the company, like internet, cloud, whose routes that you do not know in the campus, all you know is maybe a default route, that's when you use the outside border or the external world border. Right? So internal is for known routes, external is for unknown routes. Now, in many networks, we will probably have only one exit point in or out of your network. For example, let's say in a large network, you might have one particular device talking to internet, one particular device connecting to data center. We call them as internet edge, data center edge, right? That's when you can do an internal border and an external border. But for many networks, you probably have a campus core, and that campus core connects to both your data center, your internet, your WAN, everything, basically one point in, one point out. That's when you use the anywhere border, because as you can see, it connects to both known and unknown networks. Okay. Now with that, we covered a little bit of what is a fabric edge node, what is the fabric control plane node, what is a border node, the different types of border nodes, and so on. Now let's move on to the DHCP and software-defined access fabric. So let's actually take a sample network design of how your network is probably built in a traditional way. Now, you probably have a 2-tier network, right? I used a 2-tier network in the example. You could have a 3-tier network where you have your core, distribution, intermediate, really doesn't matter. Right? Then you have your centralized shared services there, like WLC and a bunch of those things for wireless. Then you might connect to, let's say, data center. It could be a traditional data center. It could be maybe ACI, VXLAN, doesn't really matter. And then you have a firewall that takes you to internet. And then you will have maybe another WAN edge that could take you to WAN, your branches, your remote sites, it doesn't really matter, right? So this is a traditional, I would say, medium to large enterprise network, especially in the European region. Okay? Now, when we convert this to fabric, this particular network becomes the fabric, right? You will now have edge nodes. Now, this could probably be your anywhere border and the control plane node. The reason the anywhere border is because now this single point of exit actually talks to internet, talks to data center, talks to WAN, your known and unknown parts of the company. Now with this, right, and before we go forward, the moment you do software-defined access, you are doing routed access in the underlay. Right? It is not layer 2 anymore. So what is the problem with routed access for our DHCP? Now, as you folks know, DHCP is more of a broadcast, right? It depends on a layer 2 network. Now, if you want to make DHCP work in a non-layer 2 network, that's when you have the IP helper addresses or the DHCP relay that you enable on your SVIs today, right? So that's how you get DHCP working over a layer 3 network. So note, SD access in the underlay is all layer 3 network. So with that, now you have your layer 3 network here, you have your fabric, you have your anywhere border, you have your control plane node. So let's say this particular client over here wants to get an IP address. There are two places where you could locate your DHCP server. One, you can probably put that in the data center, which is very common. Or you can also put it in your shared services cluster. Right? That could be another place where you put your DHCP server. But it doesn't matter where you put it, this endpoint will need connectivity, or this network will need connectivity to the DHCP server so that you can get a DHCP address from it. So let's see how that happens. So before we go there, since in SDA, we are building a fabric infrastructure, and since we are providing you mobility from one edge node to the other edge node, we have a notion called as Anycast gateway. What this means is, on every switch, you have an SVI that has the same virtual IP and the same MAC. Think of it like HSRP or VRRP. Now, HSRP and VRRP is maybe two devices. With the Anycast gateway, you can get to 1,000, 2,000, 3,000 devices, right? All have the same SVI with the same virtual IP and the same MAC. This is needed to ensure a host, when it's moving from edge 1 to edge 2, it can keep the same IP address, and it can achieve seamless end-to-end mobility. That is the Anycast gateway. Now in SDA, on that Anycast gateway, we configure the IP helper address for DHCP. Right? The moment you configure this, what happens is, when now I'm sending a DHCP request, the DHCP request comes to my edge node. The edge node is going to send a request over layer 3 to the DHCP server with its own IP, and that IP is the SVI IP. That's traditionally how DHCP works. The problem in SDA Fabric is the same address exists across all the edge nodes. Right? Now, if that happens, how do I know that the DHCP reply should come to edge node 1, edge node 2, or edge node 3? There is no way for me to know this. And that lies the problem of DHCP in software-defined access. Now, there are other architectures that we have built, especially in the data center world, called as EVP and VXLAN, where the way we solved this was every edge node will now have a separate IP address for DHCP as well, right? Meaning you have an Anycast gateway, but then let's say edge node 1 would have IP 1111, so that the DHCP request is actually sent from the secondary IP address of the SVI. In SDA, we did not want to do that, because that would mean wastage of IP space just to get DHCP working. We actually did not want to do that. So we have done some innovations to actually make DHCP work in SDA, and we are going to actually talk about that. Right? Okay. So before we move on, I also want to introduce the notion of virtual networks, aka VRFs, in Fabric. So today in Fabric, the moment you start creating SDA, you will have a bunch of virtual networks automatically created for you. One is the underlay, which is your global routing table, where your edge node, border node, your intermediate nodes, your WLC will reside in the underlay. Then you have a special VN for APs and extended nodes. And then you have your user-defined VNs for your endpoints in the overlay. So why is this important for us? The reason this is important for us is we need to ensure, since you have virtual networks that is created in the overlay, these virtual networks have access to your DHCP server. Right? And the way this is defined is, we have a notion called as a fusion router. So what does the fusion router do? So let's say you have VRF A, VRF B, and VRF C on your SD access network. Most probably, your DHCP server, which is sitting in the data center or in the shared services, would be in the global routing table. Agree? Right? So we need to ensure that using a device called as a fusion router, we route link between the virtual routing table and the global routing table to ensure your endpoints have access to the DHCP server. Right? And that's where this fusion router is needed. Okay? All right. So before we move forward, let's actually take a look at a couple of configurations on the SDS side. So assume I have a host pool, which is 10.1.18.0/24, and I have put that in, let's say, a virtual network campus, right? Some virtual network in SDA. Now I need to ensure this particular virtual network and this particular pool in the virtual network has access to my DHCP server, which is maybe sitting in the shared services. Okay? The way I give that access is, from my border node, I advertise the subnet, my local subnet, to the DHCP server. Right? So in that way, the DHCP server has a routing entry for my local subnet. The way that is done is, in the border node, we use BGP, and this is, by the way, automated from DNA Center, and we ensure that we give an aggregate address for this 10.1.18.0/24, this host pool, and we ensure that this border node will advertise that route to the shared services via BGP. But there is a bit of a problem here. Can anyone tell me why this CLI will not work? Perfect. So as the gentleman said, the reason that doesn't work is, for my aggregate address to work in BGP 101, you need a covering prefix. You need some sort of route in your routing table which has this particular subnet in it to ensure BGP will advertise it to the external world. So to ensure that happens, on the border node, we create a loopback in that particular VRF, and we use the same SVI address that we are actually using at the edge node, right? See, 10.1.18.1, and we put a loopback on the border. So to your point, to ensure that the BGP now will send a summary route to the shared services. Right? This is very important to ensure that before an endpoint comes into the network, our DHCP server has access to the subnet in the fabric. Right? Any questions before I move on? Right, perfect. Now with that, let's take a look at the DHCP flow. Now, the client sends a DHCP request. It comes to my edge node. The edge node is going to add a couple of options to it, and that is the innovation that we did. So what happens is, the DHCP request comes into the edge node. The edge node intercepts it because we have an IP helper address, and will now try to send the DHCP request all the way to the DHCP server. But it adds something in the option 82 field. What it adds in the option 82 field is the RLOC address, which is the address of the edge node in the underlay, and a VN ID. A VN ID is nothing but a VRF ID. Right? So for example, if I have VRF campus, Lisp will give it a VN ID, let's say 10. Doesn't really matter, right? Some internal VN ID. It's going to tag that in the option 82 and send it to the border node. And the border node, in turn, will send it to the DHCP server. Why this option 82 is important? we'll discuss in the next few slides, but that is what we do from the edge node. Now, to enable that option 82, we need to have these two CLIs in there, which is the IP DHCP relay information option. Again, this is automatically enabled by DNA Center, but if this was not turned on, your DHCP would not work in the fabric. Right? So once you turn on the CLI, we are going to take the option 82. We are going to add our own RLOC loopback, meaning our own unique identifier, and a VNID, and send it to the DHCP server. Sorry, my bad. Now, when the DHCP server gets it, it is first going to look at the GIA DDR. The GIA DDR is 10.1.18.1, which is basically this IP. And it's going to send the DHCP reply with an IP address from that particular subnet. That's how all the DHCP servers in the world work today, so there's no difference there. What the DHCP servers do is, in addition, they reflect the option 82 back, meaning they don't process option 82, they just reflect it back. And again, this is very standard for all the DHCP servers. So, most important note here, if you are planning to deploy software-defined access, you better ensure your DHCP server supports option 82. Otherwise, you are not going to get an IP address for any endpoints in your fabric. And that is really important here, that your DHCP server has to support option 82. If it does, it is going to just replay the option 82 back in the DHCP reply that it is going to send. Now, the reply comes to the border. Perfect. The border is going to look at that option 82, and it is going to parse the option 82 saying, hey, I got a DHCP reply back, and in the DHCP reply, I have an RLOC of 1.1.10, and I have a VNI of 10. That means this particular border node will send the DHCP reply to this edge node. That is the innovation we have done to ensure your DHCP reply is routed to the right edge node instead of going to another edge node. Right? So the way that happens is, since you have a loopback on your border node, the DHCP reply comes to the border node. Because of the loopback, we punt it to CPU. The CPU is going to dissect the information. It is going to extract the RLOC information. It is going to extract the VRF information. And then, with that information, it is going to actually send it to the edge node. So there is a couple of things to note here. On my Catalyst 9K switches and my Catalyst 6K switch, which is a border node, this is all I need. If I had an ASR 1K or an ISR 4K as my border node, you would have to have this additional CLI on the loopback that you create in the border. Now, the good thing is this is automated from DNA Center, so you don't have to worry about that. But let's say if you had a Nexus 7K as a border node, then you need to add this particular CLI, which is your IP DHCP redirect response, to all your external facing interfaces to ensure DHCP actually works in the fabric. And this CLI is not automated. So for folks who have N7K as a border or planning to have N7K as a border, again, if you don't enable that CLI, your DHCP will not work in the fabric. Right? So now that the border has parsed the DHCP reply, it is actually going to send it to the edge node. And the edge node, in turn, will actually send it to the end client. This is how we ensure in Fabric we can support DHCP request going from edge node 1, edge node 2, edge node 3, having the same SVI gateway and not having to create additional loopbacks or additional IP addresses to solve the DHCP problem. So before I move on, any questions on the DHCP piece? Yes, sir. OK, there's no way I'm going to hear you. Hold on. Yes. OK. So the question is, what is the source IP that the edge node uses to source the DHCP packet from, right? So the source is 10.1.18.1. Because on the SVI, we put an IP helper address. And keep SD out of the loop for a second. The way your DHCP works today, the moment you have an IP helper addresses, you're going to use the address of that interface to source your packet. But in SDA, therein lies the problem, right? Because the same IP exists on edge node 1, as you can see, and edge node 2. So how do I get the packet to the right edge node is a big problem, right? So again, I'm going to repeat. So in other fabrics, the way we have solved it is, we used to give a secondary address for the SVI, a unique secondary address for the SVI, and then say, hey, my DHCP now is sent from the secondary address, not the primary address. But that means in a campus, if you have, let's say, 1,000 switches, you are going to burn 1,000 IP addresses. And that is a problem. Whereas in this model, since we are tagging that option 82, the reply now comes to the right edge node. All right. So now that we have looked at DHCP, which is our first operation in any network, right? The moment an endpoint comes, it first looks for a DHCP address. Now that we have gotten an IP address, what do we do now? Okay, this is where my control plane node comes in, right? Because the moment you get an IP address, you register with the control plane node. This is independent of fabric. If you had BGP, you would try to register with the BGP. If it's ISIS, you would basically start advertising yourself into ISIS, right? The same like any protocol, the control plane node in the fabric also works the same way. So let's first look at how a wired endpoint would join the fabric. Right? So let's say a host 1 comes up in the fabric, it connects to an edge node, it gets a DHCP address from the DHCP server. It is going to send the request to the control plane node with its own IP address and MAC address, meaning the control plane node will register the host IP address and MAC address in its database table. So there is 3 types of table that a control plane node maintains. One is my IP to RLOC table. One is my MAC to RLOC table. Third one is my address resolution table. So what is an IP to RLOC table? The functionality of, or one of the functionality of the control plane node in Fabric is to keep track of where a host is located, right? Because a host could be in edge 1, edge 2, edge 3, and so on. So the IP to RLOC basically is a table that says IP 1.1.1 is behind edge 1. IP 2.2.2 is behind edge 2. That is the first table. The second table is the MAC to RLOC table, meaning we not only register the IP addresses, we also register the MAC addresses. So basically that says MAC A is in edge 1, MAC B is in edge 2, and so on. The third table is your address resolution table. Now this table is actually not populated by the edge node, but based on the information of the IP to RLOC table and MAC to RLOC table, we populate the address resolution table. Right? Now this address resolution table is actually very important. Can anyone guess why we need the address resolution table in a fabric since the fabric is routed access? Not necessarily. So the answer was it's done because the edge nodes do not know the other clients. Not necessarily. So what is the biggest here? No, it's not for proxy ARPing. So in a routed access network, what is the problem with ARP? It cannot go, right? So if I have a host or 2 hosts in the same subnet, how does ARP work? Unless the control plane node actually gives you that information, your ARP is not going to work because the routed access does not send the ARP request across, right? That is why we need the address resolution table. Otherwise, your endpoints in the same subnet would never be able to communicate to each other. That's why I think that's why. So the question is, it was assumed that the edge nodes actually do proxy ARP for everything. And my answer is that's the reason we have this session, right? So that we can clarify some of those things. No, we don't do proxy ARPing. And there's a reason we don't do proxy ARPing, and I'm actually going to cover that in a few slides from now. Okay. So these are the 3 database tables we have in our control plane node. Okay. Now, let's see how that state is populated. So the edge node sends the information or the register information to the control plane node. It populates the IP to org table saying, hey, 1.1.1 is behind edge 1. It's also going to populate the MAC table saying MAC address A blah blah is behind edge 1. Once this information has been done, we populate the address resolution table now saying, based on collating the information from these 2 tables, that the IP address 1.1.1's MAC address is so and so, right? So we actually populate the ARP table from the IP to org and the MAC to org binding. So that is basically how your wired endpoint will register this information to the control plane node. Now let's take a look at how an access point joins the fabric. So we have an access point that is connected to an edge node. The same thing happens, right? The AP will get an IP address, DHCP, the same DHCP flow. It will register with the control plane node. Now the control plane node will register the IP of the AP, edge 1, perfect. It registers the MAC address of the AP behind edge 1, awesome. And it also populates the IP to ARP binding table. Right? For an AP, there's another thing that happens. The AP will also register with the WLC, right? Because the APs always register with the WLC, right? The AP is going to register with the WLC, saying that, hey, I am a new AP, and I've come on board. The moment WLC gets the registration, what the WLC is going to do is, it is actually going to ask the control plane node, hey, I got a registration from this AP. Can you please tell me where is the AP located? Right? So the control plane node is going to look at the IP to org table, and it's going to tell the WLC, hey, this AP that you're asking me about is behind edge 1. So the WLC now maintains an AP to org table. In the next few slides, we'll go through why this table is important, right? But in the Fabric WLC, we now have an AP to org table. In essence, what this table means is the Fabric WLC exactly knows that AP1 is behind edge 1, AP2 is behind edge 2, AP3 is behind edge 3, and so on. It knows the location of every AP in the network. Okay? That's an access point joining the Fabric. Questions before I move on? Perfect. Now, once that has happened, the WLC is going to inform the access point that, hey, you are connected behind edge node 1, and that is your default gateway. So you should form an VXLAN tunnel from your AP to your edge node. Now, if you would have gone to Brkcrs 2810, we talk about in SDA, we have a convergence of wired and wireless, right? Meaning, the wireless APs are also having a VXLAN data plane. The data plane is formed because the WLC tells the AP that, hey, you are behind edge node 1, so you should form an VXLAN tunnel from the AP to the edge node 1. That is how when an AP joins the Fabric, the entire process happens. We register with the WLC, and the VXLAN tunnel is pre-created for you. Okay? Now let's look at how a wireless endpoint works in the Fabric. So we looked at wired, then we looked at access point, which is very unique, because for an access point, we ask the WLC where it is located to create the tunnel between the access point and the edge node. Now a wireless endpoint. So a wireless client joins the AP. As in a wired case, this Fabric edge node is going to register the information of the IP and the MAC to the control plane table. So we register 2.2.2 behind edge 1. We register the MAC address behind edge 1. Okay? The AP also informs the WLC of this client, right? The moment that happens, now the WLC knows that this particular AP is behind this particular edge node, right? We just looked at that in the earlier slides. Based on that, it is going to look at that table, and the WLC is going to register that information with the control plane node, meaning now not only the fabric edge node is going to tell the control plane node where is this endpoint located, but the WLC is also going to tell the control plane node where is this endpoint located. But the WLC can only populate the MAC to ORLog table. If there are wireless experts in the room, can anyone guess why the WLC can only update the MAC to ORLog table and not the IP to ORLog table? Sorry? Perfect. Because the answer is the WLC does not know IP addresses. It only tracks MAC addresses. It doesn't understand an IP address. So that is the reason the WLC populates the MAC address table of the control plane node, or the MAC to ORLog table. Now, one thing that we have implemented in SDA is, this is where we do a check. If my fabric edge node is telling that, hey, this particular MAC is behind this particular edge node, and if the WLC is giving you other information, then we deregister that client, because that's a problem, right? So assuming the WLC is also giving the right information, we update that information again in the MAC address table, and then the address resolution table is formed, where again you have an IP to ARP binding. Right? So this is how a wireless client joins the fabric and is registered to the control plane node. Okay. Now let's look at the mobility event in the fabric. Okay. So let's say your host is moving from AP1 connected behind edge 1 to AP3 connected behind edge 3. Okay. So when that happens, first the AP will detect this client. The moment the AP detects the client, it's going to inform the WLC that, hey, Mr. WLC, endpoint is trying to move from one AP to other. The WLC is going to look at that and say, hey, no, looks like this endpoint is trying to move from AP1 to AP2. So what is the location of my AP2? Well, you look at your WLC table, and then you say, well, AP2 is behind edge 3. So the WLC is going to take that information and now register to the control plane node saying, this particular MAC address blah is behind edge node 3. That information is now going to go to the control plane node. But there's a problem here. Your IP to ORLog table says that 2.2.2 is behind edge 1, because it was actually there a moment ago. And now that it has moved to this AP, your MAC to ORLog table says, well, this guy is now behind edge 3, right? But since this notification came from WLC, we always trust the WLC with this notification, and we will ensure that we update the IP to ORLog table saying that, hey, this IP is now behind edge 3. So we override the table based on the information we learned from the WLC. The moment we do this, we go and notify your old edge node and the new edge node of this move. Okay? The reason this is very, very important is, this is how you ensure your mobility in SD access works without any sort of latency or performance limits. Okay? So what we do is, this control plane node is going to tell this particular edge node, hey, you do not have this host anymore, so please deregister it from your table. The same control plane node is going to tell the new edge node that, hey, you know what? The WLC has detected a mobility move from edge node 1 to edge node 3, so you better populate your table so that by the time this host completely moves to this AP, you have all the information ready so that you can now start talking to the outside world. In this way, before I even move from one AP to the other, all the information is stored in the data plane so that, let's say if you're on a voice call, you actually roam from one AP to the other, your voice call will not break. This is one thing that we have done in SDA to ensure your mobility over a wireless network will not hit any sort of latency limits.
What is the compatibility metric between the edge, the controller, ROS, and the control plane version and DNS version?
Perfect. So the question is, what is the compatibility matrix between the edge node, border node, DNA center version, control plane node, and so on? Unfortunately, I have a slide at the very end, but the compatibility matrix is published on CCO. So if you actually go to Google, you don't even have to go to cisco.com. You search for SDA compatibility matrix. We actually take you to the page right away. And that page will list that for a particular DNA center version, this should be the switch code, this should be the WLC code, this should be the router code, and so on. Every device that we support in Fabric, we actually have detailed notes in that compatibility page. Right? If not, maybe after the session, I can actually point you to that page. Questions? Yes, sir.
So I understand that the APs are actually not in the underlay, but they are in a dedicated graph, you told us?
Yep.
Infrastructure here?
Yes. So the question is, are the APs in a dedicated VRF, or where are the APs located? So if you remember my slides, I mentioned that the APs is in a special VRF. That VRF is called as infra VM. If you look at your DNS center, it's infra VM. Now, in the backend, the infra VM is nothing but your global routing table. It is still global routing table. The reason I said a special VRF is, at some point, let's say we move the APs to, let's say, some other VRF, called maybe AP VRF or something like that. It is still in the VRF because it is being registered with the control plane node. For example, in global routing table, I can also run Lisp, meaning there is global routing table running with ISIS control plane node. There's global routing table running with the Lisp control plane node. And that is why I call it as a special VM or a special VRF. Does that make sense?
Yeah, so, but and you said the VRFs are interconnected at a special device.
Mm-hmm.
But if data, so in your forwarding table, the destination is always the edge, so not the access point. So my understanding is the packet reaches the edge node in the default VRF, and then somehow, in order to reach the access point, it has to traverse to this infrastructure VRF. So the edge node would have to have, so how does the edge node forward to the AP because if it's not in the
Got it. So the question is, this AP is in, let's say, some sort of a VRF, and the traffic from this, let's say it's coming from the outside world, from the border node comes in a default VRF, and then whatever VRF it is coming in, from there it has to actually go to the AP in a default VRF. So how does this whole routing work? Because looks like at the edge node, we have to do some sort of inter-VRF linking, right? Okay, so that was the question. So the answer is, that is actually not necessary. The reason being, even though this AP is connected, I would say, in the infra VN or a special VN on its own, that is just for DHCP traffic. Okay? Now, for every VN that you create in the fabric, there is an VXLAN tunnel for that VN between AP and the edge node. So let's say if I had 4 VNs, I would have 4 VXLAN tunnels like this. So the traffic that is coming in the overlay, let's say it is coming in VRF campus, would come to the edge node, like you rightly said, and then from the edge node, it will use the VRF campus tunnel to get to the AP. So every VRF has its own unique VXLAN tunnel. There was some.
Why do we need the WLC in this? Because when the edge is already registered the IP and the MAC of the host, why do we need a second registration from the WLC?
That's a great question. So in this whole architecture, why did you still keep the WLC? If your edge node is registering both your IP and MAC address to the to the control plane node, why do you need a WLC? We actually did not do this to sell more WLCs because a lot of people assume we are doing that. That's not the case. The reason because we did that is if I have to have a way to basically able to program all the APs without having to touch them, WLC was an easier way to do it, meaning I just go and provision the WLC with the needed config, and the WLC will go and take care of all the APs. If I took the WLC out of the picture, I would have to go and provision individual APs from DNS Center, and all the APs now have to talk to DNS Center. Imagine your SDN network, right? Let's say your DNS Center is running in the cloud. Your AP is sitting in the campus. And if I have to go talk to DNS Center to get all this information, and if I'm moving, let's say, from AP1 to AP2, I cannot guarantee roaming for voice. Right? Because your voice has to roam within, what, 40 milliseconds, 50 milliseconds, right? And if I give the power for DNS Center or the control plane node to do this, someone has to detect the configuration. Someone has to ensure you push the needed configurations. So that is why we wanted to keep a WLC, so that we don't overload the DNS Center, which is probably sitting in the data center, and impact your mobility. Does that make sense? And why we still kept the WLC?
It makes sense in case of management and configuration safety, but in sense of transmitting data, it does not really make sense to have this.
True. So, OK, I think the feedback is, well, it makes sense in terms of configuration and management of the AP. In terms of data, it does not make sense. Yes, that is true. What I meant in terms of data was, if the DNS Center had to go do some change in configuration to make the mobility work, it would be much faster if the WLC does it rather than the DNS Center doing it. That is what I meant in terms of changing the config to ensure your data plane works. And if, let's say, my DNS Center was in the data center, you add that much of latency to it, right? That's why we kept the WLC. So the question is, in that case, we could use a smaller WLC version and not use a higher WLC version. That's absolutely true, and that's why if you look at SDA, we support different variants of WLC. We support a 3504, which is our smallest variant. We support a 5520, which is a bigger variant or medium variant, and an 8540, which is our higher end variant. Right? Now, the way you look at the scale is, a 5520 can support so many number of clients, 8520, 8540, and a 5520, so on, right? So you have different flexible options to pick the WLC that you want. And we also have a newer, next-gen WLC called as, iOS or enhanced WLC that runs the same code, iOS XE, that your switch runs on. Okay. Now that we have looked at how does my control plane register a wireless endpoint, an AP, and a wireless endpoint, let's take a look at the packet forwarding in SD access. Right? So first, let's take a look at how the forwarding works within the same subnet. Okay. So let's say this is my network. I have a host 1 that is connected via wired to the edge node. I have a host 2 that is maybe wireless, and it's connected via AP to edge node 3. So in an ideal state, my control plane node or the control plane state is populated with that information. And the information is, well, this IP belongs to this edge node, this MAC address belongs to this edge node, your AR table, so everything is populated. Now imagine host 2 wants to talk to host 1. Since they are in the same subnet, the first thing the host 2 is going to do, again going back to switching 101, is send an ARP request, right? Now that ARP request comes to the Fabric edge node. The Fabric edge node is going to hijack that ARP request, and it is going to send a special message to the control plane node asking for address resolution request. Okay? Address resolution request. The control plane node is going to look in its address resolution table and is going to send the information back to the edge node. Right? Now that the edge node has the IP to MAC binding, it is going to convert it is again going to ask for a MAC request for the location of where host 1 is located. So note, earlier we sent an address resolution request asking what is the MAC address of this IP. Once we got that, we are again now asking the control plane node, hey, where is the host 1 located? Now, the control plane node is going to look at its IP to RLOG table and say, well, host 1 is behind edge 1. So that reply is going to come. And once that reply comes, we now take that information, install that into our layer 2 forwarding tables on the switch, and convert your broadcast ARP request into a unicast ARP request and send it to edge node 1. So question here, right? So we already got the MAC address of the endpoint from the control plane node. But still, we are now trying to convert that broadcast ARP to unicast ARP and send it to host or this particular host. Can anyone guess why we are still doing this? Okay. So the answer is to enable edge 1 to reply back to the edge 3. No, we could have actually used the control plane node to go notify edge 1 that, hey, you already have this MAC address that wants to talk to you. That was not the reason. Maybe we did it because of a particular problem with IPv6. Can anyone guess what that could be? Sorry? There are no broadcasts, no. Okay. So in IPv6, we have something called as options that we could actually add in your ND, neighbor discovery. Now, one of the RFC methodology that says in IPv6 is, if I am host A, and let's say you are host B, if I am sending you an ND message, you have to reply back to that message. Someone else cannot reply on your behalf. If you do that, IPv6 will break. So that is to ensure at some point IPv6 can also work in the fabric. We are taking the ARP request and actually sending it to the destination so the destination could reply back to the ARP, instead of us trying to basically take the ARP and reply on its behalf. And that's the proxy ARP reply we're talking about, right? So if we did that, IPv6 would break. That is why we still don't depend on it, and we send the ARP request to the other destination so that it can actually reply back. To ensure that when IPv6 comes in, which will in the near future, that all your options, ND options that you set, do not break any security settings for our customers. Yes, sir.
When does the ARP response in which step does the ARP response get?
Yep. So the question is, in which step does the ARP response come back? That's actually my next slide, so I'm going to get there in a minute. So now, if you can see, I got the ARP request to this edge node. This edge node is going to send the ARP request to the other edge node. That, in turn, is going to send it to the endpoint, the destination endpoint. And now, this destination endpoint is basically going to send the ARP reply, which is a unicast, because ARP reply is always unicast. And this host is going to ensure the ARP reply comes all the way back to this host. So as soon as the destination endpoint gets the ARP request, it is going to send an unicast ARP reply back to the source. Now, with this information, my host 2 has the IP to MAC binding. Now, let's say the initial ping request that had come in, or the data plane, or the data traffic, I'm going to send that over to host 1 on edge node 1, because all my tables have been populated now. Right? I have the ARP table populated at the endpoints. I have all the data plane tables populated at the edge nodes. So now my unicast forwarding in the same subnet can work end to end. Okay. So once it comes to the edge node, your VXLAN is being decapped, and then actual data plane traffic or Ethernet traffic is sent to your host. So this was forwarding in the same subnet. Let's look at forwarding across subnets. So for across subnets, again, let's say we had host 1 in subnet 1, host 2 in subnet 2. Your control plane state is formed. Everything is OK. Now host 2, let's say, wants to talk to host 1, and it sends a ping request. Since it is across subnets, and you're trying to, on the destination host, or the source host is trying to reach a destination which is not in the same subnet, it is not going to send an ARP reply or an ARP request, right? It is actually going to send a ping request directly. And if you look at the packet, the source would be its own IP. The destination would be the destination IP. The source would be its own MAC, but the destination would be the default gateway MAC, right? So default gateway MAC means it would be the MAC of this SVA address on the edge node. So once I get the ping request, since the packet is destined to me, because I'm the default gateway and I own the MAC, I'm going to basically now query the control plane node. Hey, Mr. Control plane node, where is host 1 located? That control plane node is going to reply back with the information. It's going to look at its IP to RLOG table. It's going to reply back with this information, saying that this particular destination is located behind edge 1. Once I get that, I'm going to populate the needed L3 forwarding tables, the routing information tables on my edge node, and send a packet from this edge node in VXLAN all the way to that edge node. Once the packet gets there, this guy is going to decapsulate VXLAN, install everything it needs to install in the routing table, and send the data to the actual destination endpoint. So within the subnet, we first do the address resolution. Then we send an unicast ARP to the other side, get the ARP reply, then the actual data traffic starts. Across the subnet, we don't do any ARP, right? Because it's across subnets. We just ask the control plane node, where is the endpoint located? We get the information, and then our data plane traffic starts. So that's forwarding in the subnet and forwarding across the subnets. Okay. So the question is, what is the outer layer 2 destination in this case? So this edge node is probably not directly connected to that edge node, right? It's probably connected through some intermediate devices. In this example, let's say it was some device here. So when this guy is actually trying to send traffic to that guy, if you look at your outer VXLAN header, you have your source IP, which is this RLOC. You have your destination IP, which is this RLOC. Your source MAC would be basically your MAC, I mean, whatever interface, whatever MAC you're using. The destination MAC is basically sent based on the next hop. Next hop in the underlay. Because there is a routing control plane in the underlay, which is ISIS, that is actually telling me that, hey, to reach to this particular RLOC, you have to basically maybe go through this intermediate node. That is the MAC address that you use in the outer header. Okay. So the question is that I was told that the MAC address is actually same for all the traffic. That is actually not true. So the MAC, there is an inner MAC and there is an outer MAC. So the outer MAC is always based on whatever my underlay is giving me in terms of the underlay control plane node. Inner MAC is what you're talking about, is the same basically. Did I answer the question? Perfect. Any more questions? Right. So let's take a look at the TTL functionality in the fabric. So why is this important? Now, this is important because now we have a fabric which has routed access, right? And we are actually, if you look at within the same subnet, we could have 10.1.1.1 on edge node 1, 10.1.1.2, let's say on edge node 10, and when you're traversing across an routed access fabric or routed access network, if we start decrementing the TTL, then some applications in your campus, which may be a talk at TTL1, TTL2, might start dropping because we don't have enough TTL limit left. So I'm going to explain what I mean by that. So we have two ways of doing TTL in Fabric. One we call as transparent mode, the other is non-transparent mode. In transparent mode, what we do is the TTL is not decremented at the edge nodes, at the intermediate nodes. The problem with this is, if let's say I don't decrement TTL in my intermediate nodes, my trace route won't work. Okay? Why is this important? To that gentleman's question, if edge node 1 and edge node 2 is connected between 10 hops, and if my trace route doesn't work, I have no visibility into the path. How do I troubleshoot? Okay? So that is the problem with transparent mode. Now, in the non-transparent mode, we do decrement the TTL at the intermediate node. Okay? So the good thing is, well, your trace route works because now you have visibility. Okay? Well, the bad thing is, since we decrement the TTL, let's say you have IP address in the same subnet, and for whatever reason, they were sending traffic with TTL 5. And if you had actually 10 hops between edge node 1 and edge node 2, or even edge node 10, your traffic would never reach the destination. We would drop it somewhere in between. Right? And that would suck. So the mode we used in Cisco SD Access Fabric was the non-transparent mode, so that we can actually give you visibility into the underlay. But to ensure that your TTL droppage doesn't occur because of your TTL expiring, we did a couple of very unique things with TTL. So let's say you have host 1, you have host 2, and this is trying to talk to him in the same subnet, and it sends the packet with a TTL 7. So the Fabric Edge node takes the TTL 7, copies the TTL to the inner packet, but then at the outer packet, it will add TTL value of 255. And as it passes to the intermediate nodes, the inner TTL is never touched. The outer TTL is decremented. So that now when you do a trace route, you still get visibility into the underlay. So you see from 255, we went to 254, and then we come to 253. But the inner TTL always remains the same. Now with this, the moment we come to the destination edge node, we look at the inner TTL value. If we are in the same subnet, we copy that TTL value to the packet, the Ethernet packet, and send it out. So in this way, I send it with TTL 7. I come out of TTL 7. In essence, we have emulated an Ethernet network, or a layer 2 Ethernet network, or a routed access network, right? Where you still get visibility into the underlay with trace route, and we also ensure we don't decrement TTL because we are still in a layer 2 domain.
What do you mean by you get visibility by a trace route? I mean, if I'm the user on host H1, I don't get visibility. Do I?
Okay. The question is, what do you mean by trace route visibility on an edge node? So, so let me maybe explain that with a couple of IP addresses, right? So let's say this was 10.1.1.1. Let's say this was 10.1.1.2. So you go to your endpoint. Let's say it was a Windows virtual machine or even a Windows host. You do trace CRT to 10.1.1.2. I'm going to tell you that, hey, you came to this guy, and let's say that IP was 1.1.1. From 1.1.1, you went to 2.2.2. From 2.2.2, you went to 3.3.3. From 3.3.3, you went to 4.4.4, and that's where your destination was located. That's the visibility into an underlay because of this mode. If I didn't do that, and let's say you did trace route from 10.1.1.1 to 10.1.1.2, you will get the reply back, but we won't show you that, hey, you have gone through 1.1.1, 2.2.2, and 3.3.3 to get there.
How in the fabric, the device doesn't necessarily have the ability to reach the endpoint because it's only in the default VRF and the endpoint is in whatever VRF.
Okay. So the question is, our network devices are in the global routing table, and your users are actually in the whatever VN they are in. Yes, that's true. So what I'm showing you here, and that's something that I should probably clarify, everything is done in the VN. So when you do the trace route, right, the endpoint does not care about a VN. The endpoint is connected to, let's say, VRF campus or whatever the VN it is. The trace route happens in that VRF. But since in the underlay you send the traffic with the VXLAN and you have an outer packet, which is the VXLAN header, that header carries the VN ID, which is the VRF, and that also carries the outer TTL. So meaning the underlay does not have to support VRF. This is not MPLS where you want to support VRF light. The underlay, the traffic in the underlay is still in global routing table. But since we have an VRF information, the VXLAN packet, when you actually decap at the destination node, you decap into the right VRF. That is how, even though we might be in some VRF X, we are still able to show you in the underlay what path you're taking. Right? Because the header or the VRF ID is carried in the header. It is not carried in like MPL. It's not like VRF Lite where you have to extend the VRF from hop by hop. Right? That's the difference.
I mean, at the intermediate node inside the fabric, if the TDL is down to 0, it has to reply somewhere, and that destination can only be the RLOC of the edge node. So it replies to the edge node,
Yes.
not to the host.
That is true. So I think the question is, well, if I'm doing trace route, this edge node here will basically reply with the RLOC of the edge node. That's absolutely right. In fact, that's what we want to do, right? Because that's how we figure out that you're actually going through, hop 1, hop 2, hop 3, and hop 4. So the beauty with trace route is when you send a trace route, it sends first with TTL1, it gets a reply back, then it sends TTL2, it gets the reply back, then TTL3, right? It kind of increments TTL. So the moment you do trace route, the first packet will come to this guy, it will send the whole TTL process, right? So since we are decrementing the TTL only in the outer header, we still keep getting that response back. So meaning, if let's say I send a packet with TTL1, that TTL1 will be basically copied, and since it is being decremented here, you get the response back. In that way, I know that it is going through each and every intermediate hop. We can maybe clarify after the session. Yep, sorry. Okay. So the question is, what if you are in the transparent mode and the TTL would expire? So anytime a TTL will expire, so let's say in this case, you will not hit the TTL expiry problem because your inner packet TTL we never decrement, right? So that's fine. But across the subnet, and we're going to talk that in a second, if your TTL expires, we follow the same process, right? You basically send an ICMP reply saying, hey, your TTL has expired. But within the same subnet, that would never happen because the TTL that you're getting here, right, is never decremented in the fabric. So whatever I'm getting here, I send out there. I mean, if you are sending with the TTL 0, there's nothing much I could do. But even if you send with the TTL 1, I would copy the TTL 1 to this guy and always ensure that same TTL 1 is actually sent out there. So what I get, I receive. Got it. So the question is, let's say there was some loop in the underlay, and this 254 will get to 0. What would happen? Yes, at that point, we would drop the traffic. Yep. Yes, yes. The hope is that we have 255 TTL. Hopefully, there is no 255 hops in your underlay, and there are no loops in the underlay because you're using routing. Hopefully, but yes, if there was some sort of a loop, then yes, the moment you decrement the 255 to 0, you will drop the traffic. Yes.
You said that the client will see the underlay. How? This TL is never touched. This is the TL2. The packet will make it all the way. You never get a CMP eligible of any of the hosts. Then how would that work?
Got it. So if you actually look at forwarding in the same subnet, right? So I have my TTL7, right? This TTL7 is actually copied over, and there is this outer TTL 255, right? That TTL I'm adding because I'm within the same subnet, right? Now, if I'm within the same subnet, let's say, if you are in the same subnet, when I'm trying to do a trace route, right, I should know that, hey, you know what, I am in the same subnet, so the guy that should respond back to my request should be this edge node.
So you're doing this on purpose?
In purpose, exactly. I think there was another question there at the back. Yes, sir. Got it. So the question is, in the forwarding in the same subnet, how do I get the information of the intermediate nodes? Because if I put TTL 255, it is so high that I will never hit TTL 0. That is right. The reason why we put TTL 255 in the same subnet is, I want this guy to basically reply saying, I own the destination. So it's like a layer 2 domain, right? So in a layer 2 domain, I don't want these guys to reply. And that is why we did the higher TTL on purpose. Exactly, they're transparent because in the same subnet, and we want it to be transparent. But whereas if I, let's say, didn't do this, the problem would be is, let's say this TTL, let's say it was TTL 3, right? This guy would go here, he would make it TTL 2, he would make it TTL 1, and I would never get the traffic to my destination edge node. That's why we had to emulate this transparent mode to ensure it actually works with SDA, or it works with Fabric per se. Okay. Now, this is in the same subnet. Now, if you take the same logic and apply it to across subnets, right? So let's say the forwarding across different subnets, that's when we get the same thing, right? So you get TTL 7, you go to TTL, you go to TTL 6 here, you go to TTL 5, and then you go to TTL 4. This is done because now you're not in the same subnet. You don't want to emulate a layer 2 segment here. You want to emulate a layer 3 segment. Meaning, this is when we want to show you that, hey, you are in subnet A, and the destination subnet B, and you're actually going through this multiple hop network. Right? So that's the difference between the same subnet across subnets. In the same subnet, we want to show you everything is transparent, even though you are not physically transparent. And across the subnets, we actually show you the path you're going through. So any questions before I move on to multicast? Yeah, I have to go a little bit down there. Yeah. Mm-hmm.
So I would assume all of the, because all the edge nodes would have the default gateways for all the subnets, right?
Okay. So the question was, are we going to talk about how layer 3 forwarding works in Fabric because all the destinations would have the same SVI? In fact, actually, if you look at the unicast forwarding packet walks that we had, we spoke about 2 scenarios. One is within the subnet, which is layer 2. One is across the subnets, which is layer 3. So we actually already covered the layer 3 forwarding there. So the way we did that in the slides is, if it is inside in the same subnet, that's layer 2. If it is across subnets, that's layer 3.
For TTL, you said you just copied the same.
Yep. So we actually, I don't know if I can change from here. So even in the TTL, we did both inside the subnet and across the subnets.
Okay, that's what outside subnet, you copy the inner to outer.
Yes, we don't do any of those things. Because if I did the 255, then I would lose visibility into the underlay, right? So for the across subnets, we don't actually, we just take the TTL that we have, copy it to the outer packet, and we keep decrementing it hop by hop. So let's take a look at how the multicast forwarding works in the Fabric. So for multicast forwarding, the way we deploy multicast in our network today, we have 2 options, right? It could be PIM ASM, it could be PIM SSM. Now, we could also deploy PIM BIDER, but PIM BIDER is actually not supported on the SDA network. So it has to be PIM ASM or PIM SSM. So let's first take a look at how PIM ASM works. Imagine you have a Fabric network here. You have Fabric edge nodes, you have Fabric borders, and for any ASM sort of deployment, you need a Fabric RP. Now, due to space, I'm probably showing you 1 border and 1 RP, but generally it is deployed in pairs, right? So you'd have 2 borders and 2 RPs. So let's say we have an IGMP join from this host that comes to the Fabric edge node. The Fabric edge node, since it's a layer 3 hop, is going to convert that IGMP join and send a PIM join to the fabric RP. Right? Now, the fabric RP is in the overlay space. So to your point, this happens per VRF. Right? So every VRF has to have a fabric RP. So that the IGMP join that we are getting on that particular VRF, we actually send a PIM join from the fabric edge node to the RP in that respective VRF. Okay? So the way this is going to happen is, this fabric edge node is going to ask the control plane node, where is the RP address located? Since fabric RP is in the overlay, that address is also registered with the control plane node. So the fabric edge node is going to ask, hey, where is my RP address? And it's going to send that PIM join to this fabric RP. That is how the ASM mode works in fabric. Now imagine the same thing where this endpoint is not connected via a wire, it is actually connected wirelessly to this AP. Same thing, no difference, right? The IGMP join will be sent from this host, via air to via RF to this AP. And in the VXLAN tunnel, we basically send the IGMP join to the FE node. The FE node converts that PIM join, like we did with wired, and then sends it to the fabric RP. So there's no difference between wired or wireless in terms of multicast. Okay? Now, let's say we didn't use PIM ASM, and I used PIM SSM. So in an SSM mode, I don't need an RP, because my IGMP join, which is a V3 join, already has my source information. So when this IGMP join comes to this fabric edge node, the fabric edge node has to convert that to a PIM join and send it upstream. So what this fabric edge node is going to do is, this fabric edge node is going to ask the control plane node, right, hey, where is that source located? Right? Now, let's assume for a second that the source is located behind the border node. So this fabric edge node is directly going to send the PIM join to the fabric border node. And that's how ASM versus SSM works, right? In SSM, you have an S, G join. In ASM, you have a star, G join. Okay? Now, this is how your multicast receivers join the fabric. What about your multicast source? Now, let's say this multicast source is sending traffic to your border node. Right? Now, in this diagram, I'm actually showing the source connected to the border node, but the source could probably be connected to the edge node as well. It really doesn't matter. So the multicast traffic comes to this border node. Let's say it is coming on group 239.1. Or 232, whatever group it is coming in. Now, this fabric border has to register that source with the RP, right? Source registration, like we do in PIM today. So it's going to ask the control plane node, hey, where is the RP located? The control plane node is actually going to give that information, and we register with the RP. Let's say it was in the PIM SSM mode. In the PIM SSM mode, we don't send any source registrations because there is no RP, right? So there is no source registration happening in PIM SSM mode. So this is how your multicast source works in the fabric. Now, this is the control plane side of the house. From the data plane, we have two options, and we're going to talk about both. First is head-end replication. Okay? What this means is, now that, let's say we used PIM ASM, and your source are registered to the RP, your receivers are also registered to the RP. Now you have the entire information at the RP. So there is a VXLAN tunnel that gets created from the fabric border to the fabric RP, and your multicast source data is being sent to the RP. The RP will decap it, create another VXLAN tunnel to the fabric edge node, so that the traffic is actually sent to the multicast receiver. Okay? The moment this happens, what we do is, we actually do shortest path tree failover, right? That's how PIM generally works. The moment you get the first packet in the source tree, you fall back to the shortest path tree. So the moment I get this data packet, this guy will say, hey, I'm actually getting traffic from the fabric border, but the fabric RP is sending me that. Let me fail over to the shortest path tree, and will now tell the fabric border, hey, Mr. Border, instead of sending the traffic to the RP, please send it directly to me. Right? And that's how we basically go from a source tree to a shared tree to a source tree. So in head-end replication, what happens is, let's say I have receiver 1 on FE2, receiver 2 on FE1, and both are interested in the same group. This fabric border will create two unicast tunnels to send traffic to these two multicast receivers. So head-end replication means if I have 20 receivers across 20 edge nodes for the same group, the fabric border or whoever is connected to the multicast source will have to replicate 20 times. So a unicast copy to each and every edge node in the fabric for a particular group is head-end replication. Okay. That is one way of achieving data plane multicast traffic. Now, you would agree that this is not the best resources, right? This is not optimal. So the other data plane model we have, right, again, this is PIM SSM, it's the same way, is native multicast. In native multicast, what we do is we don't do head-end replication anymore, and we use the underlay to basically replicate the traffic. And I'm actually going to talk about that. So we are going to use your underlay to natively replicate the traffic and not do head-end replication anymore. So the way we do this is, so all your existing control plane is the same, right? The PIM, the Lisp, and everything, nothing changes. Now, the way we provision this is, every multicast group in the overlay, could be PIM ASM, PIM SSM, does not matter, is basically tied to a multicast group in the underlay. If you folks have used MVPN and understand MDT data, there's MDT data tunnel and control tunnel, exactly similar. So every group in the overlay is actually assigned a group in the underlay. Now this group in the underlay is based on SSM groups only, meaning every group in the overlay gets an assigned SSM group in the underlay. So if we now actually look at the VXLAN header, the VXLAN header always has a source IP and a destination IP, right? But with native multicast, when you enable that, you will have a source IP, but your destination IP would be the underlay multicast group, right? So now if you look at the way you deploy that, there is a configuration that we push under all the VRFs in the fabric to convert yourself from a head-end replication mode to a native multicast mode. And this could be done through DNA Center. The moment I enable that, right, let's say an IGMP join comes now in the fabric edge node. This IGMP join is, let's say, coming on group 238.001. Now, as I mentioned earlier, this 238.001, assuming it's an ASM group, is mapped to some SSM group in the underlay. And let's say that was 232.009. So now, when this IGMP join comes to this fabric edge node is going to send one join, PIM join, in the overlay, one PIM join in the underlay. The overlay join goes to the fabric RP, like we discussed earlier, on the group 238.001. The underlay join actually goes on the group 232.001. So the overlay joining is happening in VRF. The underlay join is happening in the underlay, meaning it is happening in the global routing table. So this fabric RP now has a join from this fabric edge node on the 238 group in the VRF and 232 group in the underlay. Okay. Similarly, the multicast source, when it sends the traffic, let's say, to the border node will register the source in the overlay on the 238.001 multicast group, and then in the underlay on the 232.009 multicast group. So both the fabric edge node will send PIM joins. The multicast source will basically send the traffic both on the overlay group and the underlay group. Once that happens, the same methodology will follow, and again, the packet header for that would be is, so now in the unicast packet, there's IP source with source orlock and destination orlock. In the multicast, the source orlock with multicast group. There's no other difference in the packet, right? Once this happens, the traffic is now sent from the border to the fabric RP in the underlay, and from the fabric RP to the FE1 in the underlay. but this is not hidden replication anymore. The replication is actually happening in the underlay here, right? And let's say if I had client 2, let's say if I had client 2 and client 1, both wanting the traffic in the same group, this border now will not send 2 copies. It's going to send just in the underlay multicast tree, and based on the PIM joins in the underlay multicast, the underlay will natively replicate traffic. So this is how native multicast or underlay replication multicast works in SDA. Any questions on the multicast piece? Sorry, yeah. Okay. So the question is IP version 6 multicast and MLDP supported? So currently, IPv6 is not supported in Fabric. It is going to be there in the very near term. So maybe we can talk after the session on when do we plan to support it and things like that, but not currently. Yes.
How does this all scale? Because we have one-to-one mapping, underlay, overlay, multicast trees, or is there one-to-many?
Okay. Got it. Yep. So the question is, do we have an one-to-one mapping of an overlay group to an underlay group, or is it end-to-end or M-to-N mappings? Okay. Today, the way we define the configuration in DNA Center is it is one-to-one mapping. But to be honest, it really doesn't matter even if it was M-to-N, because if you remember the earlier packet, and I don't mind going here, this is still a VXLAN packet, right? So that means I still carry my VRF ID in the VXLAN header. So even though, let's say, my overlay group 1 and overlay group 2 is combined to one underlay group 1, I will still not have a problem because it is still VRF1 and VRF2, right? So when you decap into the right VRF. I think there was a question here. Got it. So the question is, who does the mapping between the overlay and the underlay group? So we do that by default in DNA Center. So what we do in DNA Center is, so let's say you have 1,000 groups, let's say, in the overlay. We can support up to 1,000 groups in the underlay. So we do overlay group 1 to underlay group 1, overlay group 2 to underlay group 2. It is all done in the default device by default. We don't have to do any settings in the controller.
But I have to specify which multicast addresses are running in my fabric chain. So it's not dynamic. I have to enable this.
Not necessarily. So what I mean by that is, the moment you tell DNA Center to switch over from a hidden replication to a native multicast, there is logic built into the devices which says, hey, if I'm getting traffic on 238 group, I will map it to 232, some 232 group. So you don't have to specify anything. The device actually automatically selects the group for you. And what I mean by that is the device has the capability to select 1,000 groups. So to that gentleman's point, if I had 1,000 groups in the overlay, I would have done 1:1 mapping. If I had 2,000 groups in the overlay, I would have done 2:1 mapping. Because then we only have 1,000 groups in the underlay, right? So then 2:1 mapping. Any more questions here? So the question is, let's say if I have a wireless network, will the AP basically get traffic, multicast traffic through the devices, or it will through CapWap from the WLC? So our wireless traffic or our data plane traffic is always using the switching network. We don't do the CapWap in SD at all. The CapWap is only for the control plane information. So your multicast and unicast traffic, whatever is coming to the AP, will always be in the switching network. Or it will always use the data plane network. I think there was one more. I'll come back. Just one more. Yeah. Yeah. Go ahead, sir.
So RP is connected to fabric in your network here. One is about existing RP and then
Yeah.
fabric network to migrate.
I was actually really expecting that question. Yeah. So the question is, I keep showing Fabric RP in my campus network. What if I already have a Fabric RP outside the network or outside the Fabric, maybe in your data center, already existing RP? So the way we do that is, and the way we recommend the design for that is, so generally, for you to enable multicast in your SDA today, you have to enable an RP. That's how our DNA Center workflow is. So assume, let's say you enable 2 RPs here, RP1 and RP2. we use Anycast RPs today. So Anycast RP means you need to have MSDP between the RPs. So if you have an existing RP outside the fabric, what we would suggest is you form an MSDP between this RP to that RP outside the fabric so that you can kind of work with the existing RP outside the fabric. Take one more and then we'll move on. That's it? All right, perfect. So I guess we're almost up. So to close with this summary, we actually looked at all the detailed packet walks of SDA. Right? Again, this is some closing slides. We have a bunch of sessions that cover SDA if you're interested. This is the entire list. It's also published on your slides if you want to download them. Right? We also have some great resources on our CVD that if you want to go look at detailed design examples, deployment guides, and so on. Right? Feedback, always welcome. As I said, there's a new session that we did. People keep talking about software-defined, and we didn't know if packet walks were good to know, not good to know. So any feedback would be really appreciated there. With that, again, complete your session survey, please. And that is pretty much it from my side. Thank you.